We can start now with the introduction to the dynamic analysis techniques. This is then the very first presentation of the 7 that are coming in the coming weeks. Let me also say that we are trying to get a kind of a series of presentations that are building up a bit the complexity of it. But let me start with a kind of a introduction that is necessary before we go into more detail. What is now dynamic? Well, as the title already said, is that we are trying to perform a thermal analysis of building components and of buildings with dynamic techniques. Well, what is then exactly dynamic? Dynamic, we relate to that as that it is involving the aspect of time. To analyze dynamic processes, we have to apply dynamic mathematical techniques. They are required to extract the specific dynamic information from the data that is coming available from experimental work. In the built environment, dynamic behavior is importantly due to the thermal mass of the object. And the object can be a component, a building component, can be a whole building, can be a whole complex of apartments. You can also understand that this dynamic behavior is coming from other environmental phenomena, and which means that we are focusing the dynamic behavior on 4 time constants. That is the yearly, seasonally, daily, hourly, and even shorter than hourly time constants. It can be sometimes minutes. But in our analysis, we are focusing only on 2 time constants. Most of the time, that is more than enough. We are also applying mathematical solutions for building physical problems. That is very important to consider that there is a combination, and I'll come back to that as well. So as said, the climatic variables are the main causes of dynamics. The plot that you see here is a yearly variation of air temperature, outdoor air temperature, and you can see that there is over 365 days that there is different variations possible during a short period, but also during the whole period. And of course, these variables, they apply not only to air temperature, but to solar radiation, to wind speed and wind direction, and even humidity. So it depends on your interest in analyzing this kind of dynamic data, if what you are considering in terms of time constants. This is data from an experimental setup. Here you can see that the solar radiation can be responsible for different temperatures over a wall component. So if you want to analyze it, you should have some physical knowledge about what is exactly happening with the solar radiation on certain properties of material. In relation to the energy performance of buildings, it is very important to understand how it is assessed by standard writers. And they have defined that the energy performance of building can be assessed by calculation or by measurement. This is also what is giving a small problem, and that is what we have introduced as the gap, the performance gap, because you expect that they should be the same, should give the same result, but in reality there is a difference between calculation and measurement. This was also one of the reasons that we have started the Annex 58 and the Annex 71 projects to understand much better where is this difference coming from between calculation and measurement. But this is the definition, as you can find it in the Energy Performance Buildings Directive. And of course, people have been looking into other ways to go around this problem and to have a somewhat more holistic approach to it. And INSPIRE, which is another big project of the European Commission, they are using administrative databases, and they give a third possibility to have an approach, kind of a backup approach, but it can be developed in a much more straight way to get some further insight in calculation or measurement results. So the EPBD is quite important for our assessment. What is also important is to understand the relation between the energy consumption and efficiency and the energy performance of a building. So in this graph, I have given that relationship. If you see these three blocks, then you might understand already where this difference is coming from. The light blue box, that is really the impact of the building fabric, the materials that are used for making a building, and of course the climate that a building is placed in. So you can imagine that the south of Europe and the north of Europe, that they have also other cultures, other materials for a building, and that is often used for making the national laws, the legislation. So this is coming from more the member state information. We call it that they have defined minimum requirements for energy performance. If you then look to the second square, where it's called building systems, their efficiency, energy efficiency is becoming important, as well as the available energy mix. If you have gas available for heating, or you have electricity for heating, etc., etc. These are the components of the calculation that is done for assessing the energy performance of a building. So these two blocks, they define the energy performance of a building. It means the building fabric, the climate zone, and the building systems, so the energy that is used to fulfill the requirements that are set by the member states. Often this assessment is done by calculating these data. If we then go and look to the big blue square, that is what is energy consumption, because people are living in the building or working in the building. They have different appliances, they behave different, they have gains, the energy gains, for example, how many people there are, how many electrical systems there are, and what is the functionality of the building. And often that kind of information about energy that is consumed by the building is coming through metering data. That part of the energy consumption is important, but it requires another way of assessing the important information in that kind of data. So we will come back to that as well. But first we will focus on energy efficiency, energy performance, before we go and look to the energy consumption of a building. So this relation you should understand. As said, that the gap is created by differences in the calculation, the method of calculating, and by the method of doing the measurements. So there is this gap, and there is a lot of proof that this gap is really not constant. We like to minimize this gap to understand much better what is going on and where to focus. The people that are working on the calculation methods, they are often to be found in the groupings from SEN or from ISO. And there are several technical groupings that are dealing with specific parts of it. So performance assessment in general is that we try to bring down the whole building energy consumption. So this is done by savings. We like also to improve the performance by improving the energy efficiency. So more efficient appliances like fridges, like ventilation system, air conditioning systems, etc. And then, of course, we like to have the overall performance assessment optimized by using more renewable energy sources on the site or maybe through the infrastructure, the energy infrastructure. What we have noticed as well is that the dynamic characteristics are becoming more prominent, which means that, for example, the use of renewable energies, they might depend on what is the amount of energy required at certain moments of the day or during the week or during the year. These dynamic characteristics, they should be understand very clearly when we do the analysis. Then we have also that the net zero energy buildings, they have also a very specific way of dealing with it. The EPBD is now proposing also the monthly calculation method, and probably in the future they will also move to daily calculation. You can understand the impact of wind energy and solar energy, that it has a much shorter time constant. Renewable energy in general is starting already at a level of the design of a building. That might also involve the energy storage for thermal mass, how to store or to avoid overheating in buildings by making a good assessment of the impact of thermal mass. Considering electricity, renewable energies, we might have in the future that electric storage could become available as an integrated part of the building as well. At the end, we consider that a building is becoming a key element in the whole energy infrastructure. And the question is, where is this balance to be defined? Is it at the building level? Is it at the infrastructure level, etc.? So these are the questions that should be answered as well. We come back to that probably in the very last session as well. Let's return to the building. Well, let's return also to the impact of the environments. First of all, if we want to deal with the analysis, we have to understand the indoor environment where the people live and work. It is often variable due to the occupants, the behavior of the occupants and what is done, carried out in the building. Then we have, of course, the variability that is due to the outdoor environment. We are living in a changing climate. We have rain, storms, we have a lot of sun, we have a lot of heat sometimes. So this is a variability that we have to deal with. And of course, there is also the uncertainty that is coming into the whole process of assessment. Because we are analyzing measured data, we have to see if the data is containing the information that we need to do a proper analysis. And often there are also phenomena, we come back to that later, that it cannot be measured. We have to deal with that as well. There is a lot of dynamic information available, but in the process of analysis, we have to understand how the information is correlated to each other in the whole process of analysis. You can understand that if the solar radiation is increasing, that also indoor temperature might increase. So how to deal with these kind of correlation aspects. Then we have also to deal with the accuracy. The accuracy is very important to see that we get the correct data into the model that we are using for our analysis. We express that as a kind of a space and time filtering, because you can have a lot of input signals for the model, but then you have to bring that back to a few input signals. And this can also have been the impact of the time filtering. If you have data of 5 minutes intervals and are trying to do the analysis with hourly data, it means that a certain part of the information you will not use, but it might also be reducing your accuracy. And of course, we have to deal with errors in the measurement, errors in the instruments that have been used. Also, the position of the sensors. Is the sensor giving the right information that you need? So there are two ways that you can follow. You can do proper testing to get the data that you are requiring for the analysis, or you do the modeling and you use other input data more from textbooks, etc., to have a proper information for the performance assessment. But anyhow, we will focus on the analysis and have the data from experimental work as the most important information source. That is why we are trying to develop a method that you should understand. You have to remember that a method for analysis is not an instrument. It is not you put the data in it and you get an answer. No, it is you who are responsible for developing a proper model that is representing your ideas about how to do the analysis. Remember that the analysis is coming from time series. They have a regular common time step, and a lot of the data that is to be used, they should have exactly the same time interval. Well, with modern techniques, computing techniques, this should not be a problem anymore. All the data that is produced is supposed to contain all relevant information to describe the physical process of heat transfer. The physical process is also defined by the physical parameters. And I emphasize it here because in the next slides we come back to that statement. In the analysis process, there are several ways to analyze the data. Very common methods are the steady states, which this is nothing else than just an average method. I will show you a little bit later how it can be done. But often the average method is used to get an idea of the expected result. And it's a rough indicator. You can understand that this kind of steady state method is not giving you the dynamic information, but it gives particular information on the thermal resistance. To have a more dynamic approach, so in order to understand a little bit the dynamics due to, for example, thermal mass, you need to have other ways. And there are two distinguished methods that you can understand easily. That is from thermal network models. We come back to that later. One of our tools that has been developed based on thermal networks, that is LORD. And LORD we have made available for the participants to this webinar. And I know that several of you, they have already requested this software tool. We have also mathematical models like the black box, the gray box models. There is limited input of knowledge is possible, and that is this continuous time method that is available. Peter Bacher will give you more information in the third webinar on it. So what is exactly the big problem for the analysis that we carry out? It is in fact how to go from many observations to a valuable result that is expected. And this can be very limited value. It can be even one data point. It can be an expression for a different period, for a whole year or for a day, etc. So you like to go from many observations, applying a method to get a limited number of results. So that is the big question. What we have expressed in this slide is how to deal with it. And in particular, the methodology, which is in the middle column, you will see what kind of aspects are important to do this kind of processing. It's not advancing. Yes, now it is. So one of the first steps that has been identified as very important is the pre-processing step of the data that has been collected. So what first thing you always have to do in this analysis process is to see if the data that you are collected from experimental work, if there are no problems in the data. So what you have to do is just plot it using Excel, just plot it and look to not expected behavior of the input signals. And the reasons of that can be a lot. Can be that, for example, a sensor is hit by solar radiation and it is suddenly completely giving different results. Can be that something, other events have been taken place, like the sensor is not working anymore, etc. So plotting is the first step. And then, of course, you can also apply the average method. And the average method gives you a first idea of the data. And there are different ways. I give you in the next slide, I give you a way how to do that. It is giving you some confidence in what you can expect. And as I said before, you will not find any dynamic information, but you find more steady state information in it. And then, of course, you can very simple kind of a testing of the data do, and by having statistical information like minimum, maximum, maximum for temperatures. You can expect that it is sometimes not going below zero, sometimes it is, like outdoor temperatures, etc. But it's a very first simple expression of it. And then, of course, you have also the reduction of the number of signals to maybe a limited one. In this case, you might have 7 indoor temperatures, but you like to have an average one of these. So that is reducing also the information on it. We call it pre-processing. This is the average method. Have a look at it because it's a quite straightforward method. You can make the length for the period, you can make it longer, you can look to certain parts of the data, and then these parts, they should be more or less the same. It's quite a straightforward idea. So what you expect by increasing length of the data, here you can see it in this graph. In the beginning, there is not much information available, so the result can go in different directions, but at a certain moment, you have enough input data available that gives you then a range where you can expect that your results should go. This is an example of a sensor that is hit by solar radiation. And in fact, the solar radiation is nicely spread over the day, but you can see that in the morning, there is a sensor that is hit by solar radiation. And then during the day, another sensor gets the full solar radiation on its sensor. And then in the evening, that's the red signal. In the evening, it might be another sensor that is hit by solar radiation. But these kind of things, they are very straightforward when you plot these signals, and then you can see, oh, there is something not really good because the sensor is not giving the information that I was looking for. Before I continue, it is very important to understand how we have defined different expressions. The expression for a model is clear. It's a mathematical description of a physical system or process. That is the model. And it is you who defines it, and it is by definition always a simplification of reality. What is then a method? Well, it's in our case, it's an identification technique, and it has two important parts. First of all, the model that was mentioned before. And secondly, it is the process of estimation parameters. And one of the estimation of the parameters can be the least squares method. So it is, in general, the application of the method is the optimization and minimization. Optimization of the mathematical model, and minimization is the error that is between the measured data and the data that is coming from the mathematical model. So that is the process. And then, of course, we have also a tool, and a tool is software. It is a software program that is made available to the user to apply a method in a very user-friendly way. LORD is such a sophisticated software program, and you can understand, once you would apply it, you can understand why it is very user-friendly. To return to the model, to uncertainty, you have to understand that you are responsible for making a model, a mathematical model. And it is you that is interpreting the process, the real process of the physics or of the building. And of course, not all people are the same. They look to the world in different ways. So you can have sunglasses with different tints. You can consider a building in very different ways. And sometimes you need some spirit to find a good model that you are happy with. In general, the approach is always that you have a set of measured data or data in general available. You have methodologies, you have selected some models, you have selected some of the mathematical equations that you are using in the analysis process. And then, of course, this data and the methodologies, they combine in tools, and they produce some results. And as said before, maybe the result is one value, but it can even be a color. It depends really on how you want to express your measurements. In this case, you look into this colorful mapping of a city where the performance of buildings are expressed in colors, and some people, they like more colors than real data. To return to another aspect that we have found during our 25 years of working in this area is that there are different approaches, different philosophies, there are different perspectives, and we distinguish already quite in the beginning that physicists and statisticians, they are not always the same ideas, same approaches. We have expressed that here in the following statement, that building physicists, they solve a physical problem using mathematics, and statisticians, they solve mathematical problems. And also we have noted that physicists, they are more interested in lower frequencies, where statisticians, they look to higher frequencies. For example, a physicist, they express a temperature, for example, 7.1, where a statistician, they may come up from the result from analysis with 0.7085, which is for a physicist not a realistic value. However, together they perform really a good team, a combination to do successful dynamic analysis. So this is important to see, that you can be a good building physicist, but you need also the knowledge, or at least the support from statisticians, and the other way around as well. So I've put here a short list again. You can look to it later in the presentation. We have tried to characterize the building physicist, and it is given here. So they are looking to physical parameters, and they are also able to cope with not measurable phenomena. Whereas a statistician, they are more interested in white noise. For example, the residue of the process, they should be white noise. And that is also the reason that they are more focused on high frequency part of the whole analysis process. You should understand that when they are working together, often the result is very promising. So the building physicist, when he meets the statistician, that works well, but of course there's always problems to overcome, where even both of them not are finding a solution. Summarizing, what is identifying the system? It is the process of using a mathematical model described of a physical system, and by creating measured data for it. Very important is to understand that the user, that might be you carrying out the analysis, you are the central part in it. You have to develop this mathematical model, and you have to decide what information you take from the measured data in order to describe the physical system. So if we express this more in a mathematical way, then you can see that there's a lot of input available to the system. That can be everything from climate data, from behavior, user behavior data, and there might be disturbance on that data, and that is what you try to get rid of in order to find the expected output from the whole analysis process. There are different ways how to deal with that, and we have that expressed in the prediction error model. That is the component of bringing down the difference between measurement and simulation data from your model. So you can have the prediction error model, and you have you can have the output error model. And in fact, they are described by the same formula, and whereas the last component of the prediction error model is put to 1. So that is what you see here. It is giving you the relation between prediction error and output error models. And this is quite a general representation. You can apply that to electrical systems, water flow systems, heat flow, transfer systems, etc., etc. This is quite a general way of presenting the analysis method. So again, what is then system identification? If you look to the bottom, there you see what the aim is. You have the measurement data, and you have the calculated data that is coming out of the set of differential equations that you have defined in the mathematical process. So you have also to understand that the physical parameters have been transferred by you in this model. So it is becoming a mathematical model, and the results of the analysis are the mathematical parameters. So at the end of the whole process, you should convert these mathematical parameters again in the physical parameters that you were looking, or that you were interested in and what you're looking for. So that is very important to realize, that the end of the system identification application is the conversion into the desired physical parameters. We are having different ways. Our tool is able to have over the data that you are using. You can have windows, so you can look to certain part of the data where certain events are taking place, and the whole minimization process of the error is then expressed, for example, in this white square that you can see. You try to minimize this error. The result is a series of residues that you can examine as well in the next step. It is a bit too much for this presentation, but we will come back to that later. So if you want to apply a mathematical model that is representing your physical object, then you should keep in mind that you have different steps of simplifying the model. In fact, a building, as we know, it is an envelope, and it is a volume. For example, in this design, we have a 3-zone building, and we have the envelope. Well, the envelope is responsible for the thermal losses by heat transfer or by ventilation, by air that is moving through the envelope. The other side of the story is also that within the envelope, you can have variable gains, and they come from solar radiation through the window. It can be how the occupants behave, and other phenomena that are creating extra thermal gains in the building. But you have to simplify it. Usually we go from 3 zones. In this case, we go to 1 zone. We try to bring back the rectangular format of the building into a kind of a sphere. And then you can understand that the simplification is reducing also your assessment of the measured data. The other thing that is very important to understand is if you take the whole building or you take a part of the building. So what we have expressed in this slide is there is an increased complexity if you go from a solid wall, for example, where you only have conduction, heat transfer by conduction, and you might have distributed thermal mass. This is one of the examples that we have given also in our data that you can find on our website. A more complex system is occurring when you have, for example, an airflow in a wall. or airflow between two windows, or etc. So the heat transfer is then combined process of conduction, radiation, and convection. So that is making already your assessment a little bit more complicated. Although it is still a wall, but the impact of the other phenomena are important. And then if you go to the bottom figure, there you have a very simplified representation of a building, of a space. There you can see also that there are some impacts of, for example, the corners of a square. You can have the impact of stratification of air temperatures. So usually the temperatures in a space, they are higher to the ceiling than to the floor. And you have, of course, the transfer through to the components, the joints of the building components, which is causing infiltration of cold air, and that is very difficult to measure. So there is increased complexity when you look to the details of your modeling work, if you want to address all the aspects of heat transfer. So sometimes you better start with a very simple model to get an idea what the expected result can be. So here I have expressed a very simple model that is describing the overall thermal transfer, the UA, as well as the transfer due to ventilation through the walls. But there is also in this expression the parameter that is giving the impact of solar radiation through the, for example, through the window. And if you want to keep that space at a certain temperature, you need to have or heating energy or cooling energy, and that is then making your balance at building level at zero. So what we are trying to do is to have this very simplified model to be using as a kind of an indication of what the thermal performance of a building can be. At the end, this mathematical representation is nothing more than this sphere where there are no corner effects anymore. There is the infiltration or the envelope ventilation aspect. There is the envelope thermal transfer by conduction, and you have the gains from solar radiation, which is the yellow arrow. And what you have done is also you have reduced the temperatures to one indoor air temperature and to one outdoor air temperature. So you can also see that a lot of the information that you have been collecting by doing measurements, that this variability is all a little bit reduced, and you have put this in a very simple input value for your modeling work. We have at the present, we have two tools available. We are using LORD, and as said before, it's a lumped parameter model. We are using thermal resistance networks to have the application of the identification process, and we have available CTSMR. There is on our website a document that you will find here on the bottom, software techniques applied to thermal performance characteristics. This is giving further information about these both tools, and there is also links where you can find these two tools for downloading, and also with data that you can use just to try your own skills on it. It is coming also with benchmark data. So if you're not sure of something, of your results. We have also exercises where we have given you the answer. We have other benchmark data available for you as well. So it is from in situ data, it is from a round robin box, and in fact that will be presented next week by Maria Jose Jimenez. And the two data series in the blue box, it's from simulated data, and it is from in situ data. You can apply that data. We have a lot of information available from previous participants who have been applying that data to their own methodologies or even to LORD or CTSMR. I will skip this one because I have been more or less addressing it. Very important is if in this whole process that you understand the available data that you have collected. How to go from measured data to data that will be used for your model. So in fact, how to go from many data from many sensors to, for example, one input temperature. Understand that then the reduction of the data, both in time as well in space, and understand also the reduction of your model, the simplification. Do a lot of exercises, so develop a skill, that is very important. And you should always ask yourself, if this is the result, why should I report this result? Are you confident in what you are presenting to someone else, to industry maybe? General approach, I've said it already before, because I'm running out of time. And I like to give my colleague as well also the time. I'm almost at the end of my presentation, but there are more slides available on the accuracy, on measurement. You will find this later on our website, the whole presentation. What I would like to mention is that after running analysis process, there is a post-processing available as well. So you should have the knowledge that you can say, well, the result of my analysis process is good enough, and you can check it by following these points that are listed here. And then, of course, at the end, as I mentioned before, you have to convert the mathematical parameters into physical ones. One of the things that is very important as well is to look into the residual. You can do residual analysis as well. You can also evaluate it from the plotting the data, and then you may have a conclusion if the real minimum that you were looking for was really the minimum, and that it is not the process error, that it is not coming into the point where the minimum is found. So this is another way of looking in it. Just plot the simulated data and the difference with the measured data, and then you might see that there is still some residue that should be included in your model in order to minimize the residue. As said before, you can find simulated data. Go to the website. The address is on the bottom given here. There you will find the building energy simulation data. There it's giving two benchmark cases that you can easily read and easily apply. So it might give you some confidence in your process of the analysis. I skip this one. I skip also the next one. Although I have to mention that this is 25 years that we are doing this kind of work with the students, and this data, you can see that the results by the participants has, well, kind of it gives insight in how important training is. If you look to the very first part of this plot, you can see that the data that we have given to the students after some training, that they are much better than in the other cases where we have given the data before the training took place. Okay, this is then my conclusion, and not only my conclusion, but the conclusion of our whole team. We said that one needs a certain level of skill to perform well, and you have to train yourself, really. Improve your knowledge by training and taking part in kind of a competition of dealing with the same data. So that is our statement. Training makes sense. This is the last slide. This is where you can find a lot of information, a lot of documents and the data. Go to dynastee.info, look to the menu item data analysis, and then in particular online training. If you have questions, please forward them to me by email, and we will deal with it in a couple of weeks. I thank you very much for your attention.